bit ahead of schedule, so what I'm probably going to do is, once we finish up with the data protection and storage, given that this is a pretty short talk, I may end up going on into the early part of the afternoon to get as far as we get before lunch and not worry about it. So, in this section, what we're going to be talking about is a bit about the practical side of the TPM's tamper resistance. This is mostly review from yesterday, just I want to mention it again because it comes up a lot when people say, I want to use the TPM for data protection. We'll talk about storage keys and binding keys and when you want to use each and the differences between them. And we'll also talk about NVRAM, which is, say, the TPM's local internal storage. So, the most frequent question I get about TPMs when it comes to data protection is, I can use it to protect my data when my machine gets stolen. Whether the answer to that is yes or no depends entirely on what your threat model is. The TPM is tamper-resistant, not tamper-proof. Governments tend to have standards about tamper resistance, and the TPM is not designed to stand up against a nation state that wants to get into your computer. However, it is great against your local thief who did a smash and grab job, because the chances that your local person who stole your laptop actually has access to a top-notch electronics lab and the knowledge to actually do careful and very discreet etching of chips is probably pretty small. So if you're talking about a threat model where I have social security numbers or credit card numbers on my laptop, and I want to make sure that when a thief steals it, they can't just make use of it, this is in fact quite a lot better than software-based disk encryption, but it's not going to be so good if you want to hand this out to somebody who's going to go get into a fight against, people in Afghanistan. So the only publicized break we've seen of TPMs, and this got put all over headlines, is, oh my gosh, TPM's broken. The answer is no. A TPM was broken into. Cost him a dozen TPMs to get one that he actually pulled the keys out of. Cost him about $100,000. That's pretty darn good for a chip that costs $1. We were all kind of shocked about that. Now, that's one brand of TPMs. We don't actually know which one, at least I don't offhand. They probably aren't all equally good, but I don't know which ones are which. And we wouldn't really use it for high-end targets. Does somebody actually know the answer to those questions? Oh, if it was an Infineon, that doesn't surprise me. So, slight digression here. Infineon is one of the, and Atmel are generally the more respected of the TPM brands. Infineon's the only one that we have reliably heard contains an endorsement key, and there are rumors that it at least sometimes contains an endorsement credential. You remember we talked about yesterday. I haven't seen one, but I haven't managed to get my hands on Infineon to look. On the other end, Broadcoms, we've seen several Broadcoms that were a little bit buggy, so whether the quality of a Broadcom is quite up to the quality of an Infineon when it comes to tamper resistance, couldn't tell you. I'd be a little surprised, but what do I know? That said, I would sort of expect a researcher who really wants to prove that TPMs are breakable to find the easiest target, but who knows? So the storage protection scenarios, the TPMs are, okay, good, it wasn't Infineon. The TPMs are designed against are evil maids, in particular the variety of evil maid attack that involves copying a hard drive and pulling the keys out at your leisure. It means you can't just walk in with a live CD, reboot your machine, and pull all the secrets out, even if your OS is protected. It's software data theft. You can't just come along and hoover up all your secrets. But the big note here is TPMs are not any good whatsoever for data protection when data is in use. TPMs are all about data protection at rest, when you are not using the data. So it doesn't matter how well I use my TPM to encrypt my data, once I've unlocked it using the TPM, TPM's not going to protect anything that's just sitting around in memory. So in general, if you're looking at software data theft as your primary threat, we generally recommend using as many small and focused encryptions as possible, because Data at rest means a lot less when you're talking about your entire hard drive, because as long as your machine is running, it's open. So that level of data protection really doesn't help at all if software threats are your issue. You know, it's good against evil maids, but you've got a Trojan, it doesn't care that it was encrypted when the machine was off. On the other hand, if you're talking about protecting software certificates, you're talking about a user password store, if you use the TPM to protect those things, your sensitive documents, then you're only risking them when they're actually in use, which is not nothing, but it is at least more constrained. And when you combine that with the TPM state verification, you can start saying things like, this particular key store, you know, I could theoretically say, and it's hard, theoretically say, is only available if I have booted into a good operating system that I reasonably trust, and by the way, Thunderbird is running. Hard, not really feasible today, but we're moving in that direction. And the more you're willing to say things like, all of my key use operations happen in Flickr. It's part of the reason for Flickr, so that you can say, Thunderbird doesn't sign my mail. Thunderbird starts a little Flickr add-on where it hands it a message and a key identity. And we go into secure mode, and Flickr would unlock your little key store and use that key to sign that mail. Now you know nothing else on the machine was stealing that key while it was in use, because you're in secure mode, you're single-threaded, you don't have any kind of memory usage attacks, and it will shut down and re-encrypt those keys again when you're finished. You get your signed mail, and your keys were not stolen. So that's a lot of what Flickr is for, is exactly that kind of single-use operation. Whether it's really feasible to do that to edit your sensitive documents, well, now we're getting into rather harder problems. But still, you can say that my sensitive document is only vulnerable when I'm using it. Somebody can't come along at 2 o'clock in the morning, steal all my data, and make use of it.
Question?
Yes.
So is Flickr still in the research phase? I couldn't remember where that...
Yes, Flickr is in the research phase.
Yeah.
You can download it. If you Google for Flickr with an E, yeah, I am so bad at this, CMU.
Okay, yep.
It's a guy named John McCune. It was originally like a master's project. There's several papers about it.
Yep.
The last paper on it seems to have been published in 2008, but they released an update in late 2011.
Oh, okay.
So it's moderately up to date.
Yep.
They do seem to have a bit of a user community around it, although not much of one. It's definitely researchware,
yep.
but it is researchware that allows you that if you were to say, in my organization is really concerned about the theft of user certificate, theft of keys used for reading email.
Right. You
could conceivably take the concepts of Flickr, take the demo code at Flickr, and give somebody spend a month.
Yeah, right.
Do this up to the enterprise standards, but no, nobody's selling it.
Right, okay.
The vast majority of TPM applications today are in that state of
I know what you mean.
yeah,
bridging that gap.
We've shown the principle. Yeah. Nobody thinks there's a profit in selling it yet.
Okay.
So, unfortunate but true. That said, storage is one of the areas where there is the most existing support for TPMs. If you look at the TPM utilities and the TPM libraries and things like Linux, there are actually, you can just go online and find instructions for using the TPM as a PKCS11 crypto hardware support for protecting your Thunderbird key store, which is why I mentioned that in particular, is because that's one of the few cases where I've actually seen step-by-step directions. The utilities are out there, and that is what the command line utilities for things like the TPM tools from IBM do.
Okay.
And similarly, BitLocker.
Right.
It's a storage application. It's one of the few cases where you can just roll out the TPM immediately. So interestingly, despite the fact that the TPM here is mostly just an incremental improvement of your software, it's where people are first saying TPMs are useful because they are looking at this sort of attack and they do want something a little stronger than software. Okay, so as I said before, the TPM is most useful when you're protecting data at rest. Doing things in bulk minimizes your advantages. And the other thing is that the TPM storage is tremendously effective if you're doing multi-part security. What you know combined with what you have. The TPM is the thing you have. The TPM will let you put passwords on data as well as on keys, which means that you can use your authorization value as the thing you know and the TPM as the thing you have and get two-part authentication for accessing your data. That's actually pretty cool. And of course, state verification with PCRs is tremendously helpful if you are not worried about the fragility of your PCR values. The more you try and use this, the more you risk inflicting a denial of service attack on yourself. And if you're doing the static group trust for measurement, one machine update can put you in a state where you're just dead in the water. Rolling back a state update such that the hashes are identical is not a trivial task. So if you are using PCR locks, you need to be very careful about what you're doing. We do strongly recommend backing up your data because those PCR locks can, in fact, just blow you away. I think there's information in this talk about backups. If there's not, remind me. I'll come back to it afterwards. So, storage keys. These are the ones that are most obviously used for data protection, given the name. They are used in a lot of different operations, like protecting keys, but TPM seal is sort of the quintessential storage key operation. It encrypts data to later be decrypted using TPM unseal. These are both about the local platform. Storage keys also are key parents. I said before that each key has its private half encrypted. That's what storage keys are for. So create wrap key takes a storage key. And as I noted before, the storage root key is a storage key. So that is, when we talk about using storage keys, you don't necessarily have to create a new one if all you want is just a TPM key. The SRK will count. You often do for special purposes, but if all you're saying is, I just want to encrypt this data locally, you don't even need to create a new key. You can just use the SRK. If you're migrating keys to a different platform, you encrypt that to the storage key because that is the new parent of the key. So you can create migratable storage keys. It tends to be a little complicated. So TPM sealing. Sealed data gives you several options. You can decide which storage key you're going to use, whether or not the data itself requires authorization, a password. So you can have potentially different authorizations for the key and the data. You probably don't necessarily want this, but you can do it. Whether you've got PCR constraints on the decryption or locality constraints on the decryption. And in this particular case, you really, really don't want to have different PCR constraints and locality constraints on the data and the key unless they are actually non-overlapping, because otherwise you now have completely useless data because the constraints are checked on the key and on the data at effectively the same time. But this does mean that even if you're using the SRK, which you really don't want to have an authorization value, you really don't want to have PCR constraints on it, you can still lock down your data much more tightly when you're using TPM seal, if you want to. Sealed data contains something called a TPM proof, which is basically a nonce that the TPM generates when you take ownership, gets stored inside, never gets revealed in the clear, and it's part of the encrypted data structure that the TPM checks when it unseals the data. If the TPM proof does not match, it will not unseal. Seal is only useful on this TPM. Even if you have a migratable storage key, the data that you sealed can't migrate with the key because of this value. It's a little weird. It's not intuitive. It happens to be true. The other thing about TPM seal is that this is what you use to prove the PCR state on encryption, not just the PCR state on decryption. That whenever you seal data, and it doesn't have to correspond with the constraints on the key itself, but whenever you seal data, the PCR constraints at sealing are stored in that integrity protected data blob. And basically, the TPM does not check anything about it. It just makes sure that the publicly readable value of those PCRs is the same as the integrity protected real value of those PCRs. And if not, it won't decrypt. So you can tell when a blob is unsealed that whether or not the PCR values that it claimed it was created under were the ones that it was created under, as well as knowing what the PCR values are now, which means that this is the way you can perform operations like saying, this data was written to disk by myself or by this machine when it was in a good state. That's actually really powerful if you're trying to do tracking. If you don't care, you can just ignore that. You have to look for it deliberately. You are not obliged to maintain that overhead. But if you want to know, yeah, was this data generated by Flickr? You know, you can determine that because if it was sealed when the machine was in a secure state, when you decrypt it, you know what the state of the machine was when it was created. So this, the data structure here is called a sealed blob. The TPM loves blobs. I promise this is actually technical language here. There you go. So when you unseal the data, you use the same storage key that you used to encrypt it, and it will verify the authorization value for the data, the current PCR values, current locality. As I said, checks that creation data to make sure that it's actually true, gives you the decryption data back. This does not actually destroy the blob. I mean, it's a blob. It's on disk. You decrypt it. The blob is still on disk. The TPM does not record, whoops, that one's been decrypted already. So I can have a blob that I sealed once, but I can decrypt every time the machine boots. That's not a problem. So once you've unsealed it, the data is in the clear, but I can use this for various purposes if I want to protect data and then only have it accessible to the machine when it's in a good state. This is what BitLocker uses. If I wanted to say there are secrets that only the bootloader has, I could do that using these sealed blobs. Protected to PCR 3 and 4 are 0. I don't care what the BIOS is, but I do know that the bootloader hasn't run yet. I can do that. And let's see, use PCR values. I wonder what I meant by that last statement. Oh, right. So data is in the clear once it's unsealed. The TPM will just hand you back whatever it was. So what that means is if all I'm doing is sealing, I'm not putting PCR constraints on it, I'm not doing authorization values, then malware on the system can just run TPM unseal freely and get the data back. There you go, it's in the clear. So the more constraints I put on my protected data, the more likely it is that I can prevent malware on that machine from getting access to that data. So if I'm just using authorization value, then you need to, then what you're looking at is now they at least need to have a password sniffer and watch you unseal it once in order to do it. If you're talking about PCR values, then you can start saying, well, I hope there's no malware here because I've got a state measurement of the machine. This is especially powerful if you're using something like Flickr, where you've got lots of locks that are guaranteed by the CPU. It's less powerful if you're just saying, well, we're running Windows. So that's storage keys for you. It's a handy-dandy utility key for protecting secret data. It's what you use to protect all of your TPM keys. You can use TPM seal operation to directly protect user data, system data, anything of that nature. And optionally, you can also use PCRs and password constraints to give you a little more protection. Seal only works on the local system, and you can decrypt with the unseal. So binding keys are the other encryption key, or more technically decryption key, that the TPM owns. Now, the paradigm for a binding key is very different than a storage key. Storage keys are all about local storage. Binding keys, anyone, anywhere can bind data that I can read. The bind operation does not assume you have a TPM at all, let alone this TPM. Anyone can perform the bind operation with software. if you look at some of the TPM driver places, like there's no TPM bind command, there is a TSS bind command. We'll get to the TSS a little later today. But the short form is software stack supports TPM operations. But you don't need to be running a TPM to run that particular command because it's just doing an encryption operation in software. You don't get fancy options with binding keys. You can still put PCR constraints and authorization values, but you're putting them on the key. You're not putting it on the block. You also don't get a default binding key with the system just because it launches like you do with the SRK. You do have to create one. So, as I said before, you do need to have a binding key with any constraints that you want. If I, as a remote party, want to impose constraints on you, I really have two options. I can say to you, make a binding key according to my desires, and then hand me a certificate for it so I know it's been created and I can encrypt to it. Or I can create a migratable binding key, send it to you, and you can decrypt it. But really, there should be one use, because after all, you can decrypt that binding key and then migrate it off to somebody else if you want, and there's nothing I can do about that, and I can't detect that. So, you know, depends on what your trust model is, depends on what assumptions you're willing to take. Those are binding keys. They're really pretty straightforward. If anyone has any questions, please let me know. That's really all binding keys are for, is that one operation, is remote decryption. So NVRAM is the local internal storage that the TPM has. There's not very much there. We're talking about 1K of memory. It's not required that there be only 1K of memory, but as with most things having to do with the TPM, the manufacturers generally take the cheap approach. So even though you could have arbitrarily much NVRAM, you don't really expect to see that in most realistic TPMs because why spend extra money? NVRAM is entirely controlled by the owner. But, as is true with most owner permissions, there is a delegation system, and I, as the owner, can delegate permission to update NVRAM, to modify NVRAM independently. So I can give somebody NVRAM permissions without giving them permissions to create an identity key and vice versa. Some sections of NVRAM are reserved. There's a particular location in NVRAM that is set aside for the endorsement credentials and the platform credentials, whether or not they exist. There's a location that those are supposed to be in NVRAM. This means you effectively have slightly less space than you think you do, unless you are willing to actually violate that big piece of the stack. Now, NVRAM space is allocated. It's not like there are N registers in NVRAM. When the owner wants to allocate space in NVRAM, they say, I want X amount of space, and that is now a region. And that region you can allocate with separate read and write access. You can allocate PCR, you can set PCR constraints on them, you can set locality constraints on them, and you can set authorization data for them. Which is to say, there's actually a pretty wide variety of permission sets you can use here. It gets even more flexible in 2.0, where you can start getting to anyone with access to this particular key can do NVRAM operations, and it gets complicated. There are a lot of different operations for setting NVRAM. I'm not planning on getting them into that today because there's several different commands. You probably don't really care about the details. If you do, they're actually pretty straightforward in the spec. There you go. If somebody really wants to beg me to look that up over lunch and come do a talk on it this afternoon, I'm willing to do it, but you probably don't care that much, and you can just look up the reference. So NVRAM is tremendously helpful if you're using it for reference data. If you put a hash in there that allows you to verify that data on disk has not been modified. So if I am the system owner and I want to say, you should always verify software using a particular public key that is my public key. How do I know that that public key hasn't been modified? Well, I can stick a hash of that public key in the NVRAM. Only the owner can write that. Malware can replace the public key on disk as much as they want, but they're going to have a lot of trouble changing the NVRAM. So very, very useful for sanity checking. Anytime you want to do verification like this, hashes and NVRAM are tremendously powerful. And it's also very useful if you have high value data that you really don't want to be deleted. If I have a particular key that for some reason I don't want to be owner evict, and I never want it to be deleted, I can put it in an NVRAM and lock it down. That said, remember how tiny this is. The more you put data in it instead of integrity checking data in it, the less room you have to do anything. And I'll be perfectly honest, I'm not entirely sure just how many things you can put in there and still have much use out of it. But if you have one or two things that this particular, it's critical that this system have, never get modified, never get overwritten, this is a way to do it. If you have particular data that you want to have strong access control policies for, even if the machine boots into a different operating system, this is one way to do it. So there's one other problem with NVRAM. In addition to how limited the space is, there are a limited number of writes in the lifetime of the NVRAM. And we don't know how many they are. It's probably at least 10,000, but we don't know how many. So if what you're using this for is, I have a hash of the current expected owner public key, I have a hash of my corporation's root certificates, so I can make sure those have been modified with. Yep. Yes, those may update every so often, but really not that frequent. On the other hand, if I have an application that is going to try and do integrity protection every time the application data updates, and that application data may in fact update several times a day, or worse yet, several times a minute, you may in fact burn out your NVRAM by updating it very frequently. Where the line is as to how frequent is a problem, we don't know. We wish we did, but we don't have any data as to how many writes real-world NVRAM actually takes to burn out. If you are doing something that does have lots and lots and lots of updates, and you care about integrity protection, we actually recommend looking into things like the monotonic counter, which is obliged to be updatable, I think, 10 times a second for at least 10 years, something like that. So the monotonic counter updates you are realistically never going to burn out. It's designed to not realistically be burn-outable, whereas NVRAM is. So there are ways to use monotonic counters less well, less conveniently than NVRAM, but if you are talking about once-a-second updates, you can't use NVRAM without running into problems. So in short, the TPM is very good at data at rest protection. We can use storage keys for data on this platform, and that gives us a lot of different protection options, including PCR constraints and locality constraints, authorization values. Binding keys protect data from anywhere with a little bit less flexibility. The more constraints you want, the more out of the way you have to go with creating your binding key. And NVRAM is very good for protecting limited high-value data, like integrity verification. It can be used for other things, but the more you use it, the more risky it gets because it is very small and does burn out. So, any questions on storage? This break we've seen of TPMs, and this got put all over headlines is, oh my gosh, TPM's broken. The answer is no. A TPM was broken into. Cost him a dozen TPMs to get one that he actually pulled the keys out of. Cost him about $100,000. That's pretty darn good for a chip that costs $1. We were all kind of shocked about that. Now, that's one brand of TPMs. We don't actually know which one, at least I don't offhand. They probably aren't all equally good, but I don't know which ones are which. And we wouldn't really use it for high-end targets. Does somebody actually know the answer to those questions? Oh, if it was an Infineon, that doesn't surprise me. So, because the chances that your local person who stole your laptop actually has access to a top-notch electronics lab and the knowledge to actually do careful and very discrete etching of chips is probably pretty small. So if you're talking about a threat model where I have social security numbers or credit card numbers on my laptop, and I want to make sure that when a thief steals it, they can't just make use of it, this is in fact quite a lot better than software-based disk encryption. But it's not going to be so good if you want to hand this out to somebody who's going to go get into a fight against, people in Afghanistan. So the only publicized, slight digression here, Infineon is one of the, and Atmel are generally the more respected of the TPM brands. Infineon's the only one that we have reliably heard contains an endorsement key, and there are rumors that it at least sometimes contains an endorsement credential. You remember we talked about yesterday. I haven't seen one, but I haven't managed to get my hands on Infineon to look. On the other end, Broadcoms, we've seen several Broadcoms that were a little bit buggy, so whether the quality of a Broadcom is quite up to the quality of an Infineon when it comes to tamper resistance, couldn't tell you. I'd be a little surprised, but what do I know? That said, I would sort of expect a researcher who really wants to prove that TPMs are breakable to find the easiest between them. And we'll also talk about NVRAM, which is to say the TPM's local internal storage. So the most frequent question I get about TPMs when it comes to data protection is, I can use it to protect my data when my machine gets stolen. Whether the answer to that is yes or no depends entirely on what your threat model is. The TPM is tamper-resistant, not tamper-proof. Governments tend to have standards about tamper resistance, and the TPM is not designed to stand up against a nation state that wants to get into your computer. However, it is great against your local thief who did a smash and grab job, because ahead of schedule, so what I'm probably going to do is, once we finish up with the data protection and storage, given that this is a pretty short talk, I may end up going on into the early part of the afternoon, to get as far as we get before lunch and not worry about it. So, in this section, what we're going to be talking about is a bit about the practical side of the TPM's tamper resistance. This is mostly review from yesterday, just I want to mention it again because it comes up a lot when people say, I want to use the TPM for data protection. We'll talk about storage keys and binding keys and when you want to use each and the differences.